Saturn has fascinated humans since we first looked up and realized something massive was moving across the night sky, something slow and ancient and almost deliberately mysterious. For thousands of years, this gas giant remained a puzzle wrapped in distant light, visible to the naked eye, yet impossible to truly understand. What is Saturn really? Where did it come from? How does it keep spinning with those impossible rings circling it like a crown, made of ice and rock? These questions have driven scientists and philosophers and curious humans into obsession. And the deeper we dig, the stranger the answers become. Saturn is not just another planet. It is a system unto itself, a place where the normal rules of planetary behavior seem to bend, where mysteries pile on top of mysteries, each one revealing something more bizarre than the last. The more we learn about Saturn, the more our understanding evolves, and yet it seems like every answer just opens more doors, like Saturn is deliberately keeping its deepest secrets locked away from prying human eyes. Tonight, we begin to unravel them, one revelation at a time. What we discover about Saturn will challenge everything you thought you knew about how planets work, how rings form, and what conditions might be necessary for life to exist in places we never expected. Ancient astronomers knew Saturn long before they understood what they were looking at. The Assyrians called it Lubadzagush, which means the oldest of the old, because they watched it move so slowly across the backdrop of stars that it seemed almost ancient compared to everything else in the sky. Unlike the faster-moving planets like Venus and Mercury, Saturn crawled across the heavens so gradually that a human lifetime might not reveal the full arc of its journey. Imagine standing at the same location every clear night for a year, marking the position of a planet against the background of stars, and seeing it barely move at all. This slowness itself was mysterious. What kind of celestial body moved with such deliberation? The Babylonians, perhaps the most sophisticated astronomers of the ancient world, tracked Saturn carefully over centuries, recording its positions and noting its patterns. The Egyptians made observations of Saturn's positions and incorporated them into their understanding of cosmic cycles and the passage of time. The ancient Greeks, particularly those following the mathematical traditions of astronomy, observed Saturn's movements with remarkable precision for the era, developing geometric models to predict its future positions. They could see it clearly on dark nights, a pale golden disk that commanded attention without demanding it. The fact that Saturn was visible to the naked eye made it significant in ancient astronomy. Yet its distance and its slow motion kept it at arm's length, forever foreign, forever strange. It was the farthest planet that human eyes could detect without assistance, the boundary marker between the known and the unknowable, the limit beyond which the universe seemed to stretch into infinity. Ancient cultures built entire cosmologies around Saturn's movements, assigning it religious meaning and temporal significance. In many traditions, the slow-moving planets were considered more important, more weighty, more capable of influencing human affairs because they moved with such gravitas, such careful deliberation. The Romans named it after their god of wealth and agriculture, giving it weight and importance in their pantheon, associating the planet with harvest cycles and the passage of seasons. In Hindu astronomy, Saturn held a crucial place in calculations about time and the ages of the world, the great cosmic cycles that governed creation and destruction. In Chinese astronomy, Saturn was tracked and observed with careful precision, incorporated into systems of divination and prophecy. In Islamic astronomy, Saturn was observed and studied, its position noted for purposes of timekeeping and religious observance. Each civilization that observed Saturn added its own layer of mystery, its own interpretive framework. What they shared was a sense of awe, before something so distant, so slow, so fundamentally other. The planet did not reveal its nature to ancient observers. It simply existed, moved, and waited. Nothing in the ancient world could have prepared anyone for what Saturn actually was. The observations were careful and detailed, but they were also limited by the naked eye, constrained by human eyesight's natural limitations and by the absence of any optical aids. Astronomers could measure the angle of Saturn's position relative to other stars with impressive accuracy, using angular measurements and geometric calculations. They could track its retrograde motion, the apparent backward movement that confused early astronomers until they realized the Earth itself was moving. They could note when Saturn disappeared into the sun's glare and reappeared on the opposite side of the sky, tracking the length of its disappearance and inferring something about its distance from Earth. They could even attempt to measure its brightness, noting variations over time. But they could not see the rings. This absence would remain until human technology finally advanced far enough to reveal what had been hiding in plain sight for millennia, a feature so distinctive, so defining, yet so invisible to unaided eyes. Ancient astronomy was an exercise in geometry and prediction, not understanding. Astronomers created models of planetary motion, trying to explain why Saturn and the other planets moved the way they did. Ptolemy developed his geocentric model, with Earth at the center and Saturn orbiting at the outermost reaches. Later, as heliocentric theory emerged, Saturn's position in the solar system began to shift in human understanding. It was no longer the boundary of creation, the farthest extent of God's work. It was simply one planet among several, orbiting a sun that was itself apparently unremarkable. Yet this shift in understanding did not diminish Saturn's mystery. If anything, it deepened it. What was this distant world made of? How did it stay together? What caused it to move the way it did? Ancient astronomers could document Saturn's behavior, but they could not explain it. The planet remained what it had always been, a mystery wrapped in distance and time, visible enough to observe but far enough away to keep its secrets hidden. It would take the invention of the telescope to begin changing that relationship. For the first time, human observers could see beyond the limits of the naked eye, could peer at the heavens through glass and metal and magnification. This was the moment when Saturn's true nature would finally begin to reveal itself, though even magnification would not fully explain what observers were seeing. When Galileo Galilei pointed his telescope at Saturn in 1610, he saw something that should not have been there. The planet appeared to have companions, or perhaps ears, or something that looked almost like a triple planet fused into one strange shape. Galileo's telescope was primitive by modern standards, but it was revolutionary for his time, magnifying the heavens 8 times and pulling in details that no human eye had ever witnessed. What he saw around Saturn confused him entirely. The rings were so strange, so unlike anything else in the solar system, that Galileo struggled to describe what he was observing. The optical quality of his telescope was poor enough that the rings appeared as blurred, distorted shapes, ambiguous in their exact nature. He eventually wrote that Saturn had an appendage, like a handle attached to it, a companion that orbited alongside the main planet. This was his attempt to make sense of something his mind had no framework to understand. The rings did not look like rings. They looked like extensions of the planet itself, or perhaps like a moon pressed flat against Saturn's sides. Galileo sketched what he saw and published his observations, creating great confusion in the astronomical community. How could a planet have appendages? What was this strange triple structure? Galileo could not conceive of the actual explanation because nothing in human experience matched it. The physics of how rings could form, how they could persist, what they were made of, none of this existed in any scientific framework of the early 1600s. Other astronomers looking at Saturn through their own telescopes reported similar confusion. Some thought the appendages were satellites in unusual orbits. Others thought the planet was changing shape, expanding and contracting. A few wondered if what they were seeing was simply a trick of the telescope, a flaw in the glass creating an illusion. The mystery only deepened as telescopes improved and observations became more precise. Different observers made contradictory observations at different times, leading to debate about whether the features were permanent or temporary, whether they rotated around the planet or remained fixed. In 1656, Christian Huygens, a Dutch astronomer with superior telescopes, had a breakthrough insight. What Galileo and others had interpreted as handles or appendages or strange companions were actually a ring circling the planet. Not a single moon, but an actual ring made of countless tiny particles, or perhaps a solid band. This was utterly alien to anything known in astronomy. No other planet had such a thing. No theoretical model explained how a ring could form or persist. Huygens published his discovery cautiously, understanding the revolutionary nature of what he was proposing. Huygens had cracked part of the code, but the mystery of Saturn's rings was far from solved. In fact, a deeper mystery was beginning to form. If Saturn had a ring, where had it come from? What was it made of? Why was it there? These questions would occupy astronomers for centuries to come. The observation that Saturn had a ring was revolutionary, but it immediately raised more questions than it answered. Telescopes continued to improve throughout the 17th and 18th centuries, becoming longer, more carefully ground, more precisely calibrated. Astronomers discovered that Saturn's rings were not actually continuous. There were gaps in them. There appeared to be multiple rings, separated by dark lines that became known as divisions. The largest and most prominent division was named after Jean-Dominique Cassini, who observed it carefully and documented its existence with precision. Cassini also discovered several of Saturn's moons, understanding that Saturn was not a single object but a complex system. Saturn was becoming increasingly complex, increasingly mysterious. Each advancement in telescope technology revealed new details, new complications, new puzzles. The rings were not simply a ring. They were a system of rings, possibly hundreds or thousands of them, with gaps and divisions and features that suggested some kind of dynamic process was at work. Waves and ripples appeared in the rings, suggesting gravity was shaping them. Ring spokes appeared and disappeared, appearing to rotate with the planet's magnetosphere in ways that made no theoretical sense. Astronomers began to realize that Saturn was not a static system, but a dynamic one, constantly changing and evolving. By the time spectroscopy was invented in the 19th century, allowing astronomers to analyze the light reflected from Saturn's rings and determine their chemical composition, it became clear that the rings were made primarily of water ice, crystalline ice similar to Earth's glaciers and polar ice caps. Billions upon billions of tiny ice particles, ranging from dust-sized specks to chunks as large as mountains, all orbiting Saturn in organized patterns. Some particles are isolated grains floating in the void. Others have clumped together to form larger bodies that range in size from boulders to moonlets. This raised yet another mystery. How could ice particles maintain such precise, stable orbits over billions of years? What kept them from colliding and clumping together into larger bodies? What maintained the gaps between the rings? What dark material contaminated the ice, giving some regions different reflectivity and suggesting a complex history of impacts and chemical alteration? The Cassini spacecraft provided unprecedented detail, flying through Saturn's system from 2004 to 2017 and sending back data that revolutionized understanding. Cassini flew within the ring plane during its grand finale orbits, measuring particle properties directly, detecting the rain of material falling into Saturn's atmosphere at the rate of thousands of kilograms per second. Cassini's instruments analyzed the composition of ring particles, discovering organic compounds and confirming the water-ice composition. Cassini's gravity measurements revealed the interior structure of Saturn, its rotation rate, the distribution of mass. Cassini's camera system sent back thousands of images showing the intricate structure of the rings, the dynamic processes shaping them, the interactions between particles and moons. Yet even with this advanced technology, many questions remained unanswered. The mystery had evolved and deepened, but it had not been solved. When ancient astronomers assigned names to the planets they observed, they worked with limited information and a sense of cosmic significance that we might find difficult to access today. Saturn received its name from the Roman god of wealth and agriculture, a deity of the harvest and of time itself. The Romans called Saturn Saturnus, derived from the root meaning to sow, directly connecting the planet to agriculture and the eternal cycles of planting and harvest. This god was associated with the Greek Kronos, the Titan who ruled during the mythological Golden Age, before Zeus and the Olympians took control, the god of time and the passage of ages. There was something about the slow, methodical movement of Saturn across the sky that seemed to fit with Saturn the god, ancient and primordial, the keeper of time and the cycles of the seasons. The Romans celebrated the Saturnalia festival in Saturn's honor, a celebration that temporarily inverted normal social hierarchies and celebrated the deity's gift of abundance. This naming was not arbitrary. It emerged from a genuine sense that Saturn possessed some special quality, some weight and significance that distinguished it from other wandering stars. The name stuck through centuries of cultural changes, religious shifts, and scientific revolutions. Even as our understanding of what Saturn actually was transformed completely, the name remained, a linguistic anchor to the ancient world's intuitive recognition that this planet was important, was different, was somehow emblematic of age and distance, and the deepest reaches of the vis-ible universe. Other cultures had their own names for Saturn, reflecting different mythologies and different ways of understanding the cosmos. In Arabic, it was called Zuhal, meaning the hidden one, another acknowledgement of its distant and obscured nature. In Persian, Saturn was known as Kayvan. In Hebrew, it was Shabbatai. In Chinese astronomy, Saturn was associated with one of the 5 elements, Earth, and held a specific position in the celestial order, representing wealth and wisdom, but also hardship and testing. In Japanese astronomy, Saturn was called Tu-Shing, which literally means Earth star. In Hindu cosmology, Saturn, known as Shani, held a complex and often fearful role, sometimes malevolent, sometimes instructive, always powerful and commanding respect. Shani was said to test humans and bring about karmic consequences. Each name reflected a culture's attempt to categorize and understand this distant world, attempting to fit it into their existing frameworks of mythology and understanding. The naming of Saturn was an act of claiming it, of making it part of human knowledge, even though it remained fundamentally distant and mysterious. As the scientific age emerged, the casual naming practices of ancient cultures gave way to more systematic approaches. Chemical elements and features of planets received names from classical mythology, creating a coherent naming system across the scientific community. Saturn's moons received names primarily from classical mythology and Shakespearean characters, creating a complex naming structure that reflected both scientific practicality and historical continuity. The International Astronomical Union eventually standardized all planetary nomenclature, ensuring consistency across different cultures and languages, creating a universal system that transcended local traditions. Yet even with this standardization, Saturn's name itself remained unchanged, still evoking that ancient god, still connecting modern observers to astronomers thousands of years in the past. The name Saturn carries weight that newer discoveries lack. It connects us to a moment when humanity first looked up and recognized something vast and distant, and gave it a name that would endure through all subsequent discoveries and revisions of understanding. The planet itself had no knowledge of this naming, no awareness that humans were assigning it significance and placing it within their cultural frameworks. But the act of naming was profound nonetheless. It meant that Saturn had become part of human thought, part of how we organize and understand the cosmos. The name was a bridge between the ancient world and the modern one, a linguistic continuity that persisted even as everything we thought we knew about Saturn was revolutionized by telescopes and spacecraft and mathematical models. Saturn's position in our solar system is the sixth planet from the Sun, positioned between Jupiter and Uranus, orbiting at an average distance of about 886 million miles from the Sun, or about 9.5 times the distance that Earth orbits from the Sun. This distance makes Saturn a fundamentally different world from the inner planets, positioned where the Sun's gravity is weaker, where orbital mechanics follow different rules. It receives so little heat from the Sun that scientists once assumed it would be a frozen, dead place, a ball of ice orbiting in eternal darkness, essentially a lifeless world beyond the realm of solar warming. Yet observations revealed something far more complex and unexpected. Saturn is not cold and dead. It is active, dynamic, turbulent in ways that seemed impossible for a world so distant from the Sun's warmth. The planet orbits the Sun once every 29 Earth years, making a single complete orbit around our star take nearly 3 decades to accomplish. This means that if you were born on Saturn, you would not complete a single year of life before reaching old age by human standards. It would take nearly 30 years for Saturn to return to the same position relative to Earth that it occupied when you were born. 30 years during which you would grow old, your hair would turn grey, and your children would become adults. This extended orbital period explains why Saturn moves so slowly across the night sky, why ancient astronomers called it the oldest of the old. The further a planet is from the Sun, the slower it must orbit to maintain a stable trajectory. This is a consequence of orbital mechanics, gravity, and the way celestial bodies interact. Objects in closer orbits must move faster to balance the Sun's gravitational pull. Objects in distant orbits can move more slowly. Mercury, closest to the Sun, zips around our star in just 88 days, completing several orbits during the span of Earth's single year. Venus takes 225 days. Earth takes 365 days. But Saturn, so far out that it receives only about 1/100th of the light and heat that Earth does, takes nearly 30 times as long to complete one orbit. This vast difference in orbital periods creates a sense in which Saturn occupies a different temporal realm than Earth. When we observe Saturn, we are observing a world operating on a different timescale, a different rhythm, almost a different reality. A Saturnian year is a 29-year cycle that we measure in Earth terms. Yet a Saturnian being, if such a thing could exist, might experience that year as completely normal, divided into seasons the way ours are, but with each season lasting more than 7 Earth years. Imagine seasons that stretch across a human lifetime, seasons so slow that their effects accumulate gradually, subtly, almost imperceptibly. Saturn is not alone in its orbit. It has gravitationally captured and retained numerous moons, currently estimated to number between 140 and 274, with new discoveries continuing to be announced as detection technology improves. The most massive and notable of these are Titan and Enceladus, both of which harbour internal oceans beneath their frozen surfaces and may possess the conditions necessary for exotic forms of life. Titan is the largest moon in Saturn's system, larger than the planet Mercury, and possesses a dense atmosphere that only one other moon in our solar system, Jupiter's Ganymede, can match in complexity. Titan has methane lakes and oceans at its surface, liquid hydrocarbon bodies that make it the only place besides Earth known to have stable bodies of surface liquid. Other notable moons include Appendages, with its distinctive equatorial ridge that makes it look like a walnut split in half, a feature that remains poorly understood despite decades of observation. There is also Mimas, whose massive impact crater makes it resemble the Death Star from Star Wars, a resemblance so striking that it has made Mimas recognizable even to people who are not astronomers. The crater is so large relative to Mimas's size that the impact that created it nearly shattered the moon entirely. Then there is Enceladus, a small moon that orbits within Saturn's E-ring and shoots plumes of water vapor and organic compounds from its south polar region, potentially harboring a subsurface ocean that could support life. These diverse worlds within Saturn's system represent different geological histories, different compositions, different opportunities for exploring how moons evolve and what conditions might sustain life. Saturn's entire system of moons, rings, and the planet itself operates as a miniature solar system, a small-scale model of planetary formation and orbital mechanics. The rings are perhaps Saturn's most distinctive feature, but they are only the most obvious part of a complex system. The planet itself possesses a magnetic field, though weaker than Jupiter's powerful magnetosphere, and structured differently in ways that still surprise scientists. Saturn's magnetosphere, the bubble of magnetic influence surrounding it, creates unusual electromagnetic phenomena and interacts with the planet's rings in ways that are still not fully understood. Charged particles flow in complex patterns. Plasma waves oscillate. Magnetospheric currents generate heat and light. The rotational period of Saturn's interior differs from its visible atmosphere, a situation called differential rotation. This means that the planet is not spinning as a uniform solid body, not rotating as a rigid object the way a spinning ball spins. Instead, different layers rotate at different speeds, like concentric rings of a record player all turning at different rates. The visible cloud tops rotate on a period of about 10 hours and 40 minutes near the equator, but the deep interior, as measured by gravity data from the Cassini spacecraft's final orbits, rotates with a period of about 10 hours and 33 minutes. This difference is small but significant, indicating that Saturn's interior is not rigidly coupled to its atmosphere. Massive jet streams circle the planet, particularly in the equatorial regions, reaching wind speeds of up to 1,800 kilometers per hour, or about 1,100 miles per hour, the fastest winds of any planet in the solar system. These winds are not driven by the sun's heat, not powered by solar radiation heating the atmosphere. Instead, they are driven by Saturn's internal thermal engine, the enormous amount of heat radiating from deep within the planet. This is a fundamental mystery that has occupied planetary scientists for decades. Saturn, so far from the Sun that it receives minimal solar energy, maintains and drives its turbulent atmosphere through internal heat generation. How this works, why Saturn has so much internal heat, and how it is transported to the atmosphere and released remain active areas of scientific investigation. Saturn's axial tilt is approximately 27 degrees, similar to Earth's 23-degree tilt, which means Saturn experiences seasons just as Earth does, though each season lasts more than 7 Earth years instead of 3 months. The tilt is believed to have been caused by gravitational interactions with other planets in the early solar system, or possibly by the collision with a large moon that we discussed earlier, creating an asymmetry in Saturn's gravitational structure that persists to this day. Observers on Saturn, if they existed, would experience dramatic seasonal variations as the planet orbited the Sun, with one pole tilted toward the Sun and then the other, creating patterns of light and shadow that would be utterly alien to human experience. The North Pole would experience a long summer lasting 7 years, while the South Pole experienced an equally long winter, creating climate patterns on timescales incomprehensible to human civilization. The planet itself is flattened dramatically, with its polar diameter being only about 90% of its equatorial diameter. This flattening, more extreme than any other planet in the solar system, results from Saturn's rapid rotation combined with its extremely low density. Saturn is made almost entirely of hydrogen and helium, making it the least dense planet in our solar system, less dense than water. If Saturn could be placed in a bathtub the size of a small ocean, it would float, a fact that fascinates both scientists and the public imagination. This low density, combined with Saturn's rapid rotation at its equatorial regions, causes the planet to bulge outward dramatically at its equator and flatten at its poles, creating the distinctive oblate spheroid shape we observe through telescopes. The difference between equatorial and polar diameters is more than 10,000 kilometers, a tremendous distortion. Saturn's internal structure, beneath the visible cloud layers, remains largely mysterious, despite centuries of observations and space missions. The planet has no solid surface, no solid core confirmed by direct observation. Instead, the planet is believed to transition gradually from a gaseous atmosphere to a liquid interior composed primarily of hydrogen and helium, possibly with an icy core deeper down, though the exact structure is debated among planetary scientists. Pressure increases with depth until the hydrogen becomes liquid, then metallic, then possibly assumes even more exotic states of matter under the extreme conditions at Saturn's core. The pressure at Saturn's core may exceed 1 million atmospheres, creating conditions that have never been replicated in Earth laboratories. Temperature climbs steeply with depth, reaching an estimated 11,700 degrees Celsius at the core, hot enough to rival the surface of the Sun itself, a fact that contradicts the assumption that a planet so far from the Sun must be cold. This interior heat is perhaps the most significant mystery about Saturn's structure and composition. The planet radiates 2.5 times more energy than it receives from the Sun, an enormous excess that cannot be explained by current models of planetary physics relying on solar heating alone. Something deep within Saturn is generating tremendous heat, pumping it outward continuously. Scientists believe that helium in the upper layers is precipitating downward, forming liquid helium droplets that fall through the hydrogen layers like raindrops, converting gravitational potential energy into kinetic energy and then heat through friction as they descend. This helium rain has been falling for billions of years, slowly depleting the upper layers of helium and gradually changing Saturn's atmospheric composition. The evidence suggests this process began about 2 billion years ago, when Saturn had cooled sufficiently for helium to condense rather than remain in gaseous form. Since then, a steady shower of helium has been descending through Saturn's interior, a continuous process that may continue for billions of years into the future. This mechanism explains why Saturn's atmosphere contains less helium than Jupiter's or even the Sun's atmosphere, a deficit that puzzled scientists for decades until this explanation was developed. The exact process and its role in Saturn's total energy output remain subjects of active research. The magnetic field of Saturn is another puzzle that has challenged scientific explanation. Saturn's field is generated by circulation currents in the metallic hydrogen layer that composes Saturn's deep interior, the same layer that probably contributes to the planet's heat generation. The calculated electrical conductivity of this region is such that slow circulation currents would produce sufficient dynamo action to generate the observed magnetic field. Unlike Earth's field, which is offset from Earth's rotational axis by about 10 degrees, Saturn's magnetosphere appears to be nearly perfectly aligned with its rotational axis, creating an unusual situation where the magnetic poles are almost perfectly aligned with the rotational poles. Saturn's magnetosphere is asymmetrical, offset from the planet's rotational axis in ways that are not fully understood. Unlike Jupiter's powerful magnetosphere, which is one of the strongest in the solar system, Saturn's is weaker and more variable. The interaction between the magnetosphere, the rings, and Saturn's moons creates a complex electromagnetic environment that continues to surprise scientists with new phenomena and unexpected behaviors. Charged particles spiral along magnetic field lines. Plasma waves propagate through the magnetosphere. Radio emissions sweep across the planet as it rotates. Every measurement and observation of Saturn reveals new layers of complexity. The planet that ancient astronomers could only watch slowly moving across the sky has become a world of intricate detail, mysterious processes, and fundamental physics that stretches human understanding. Despite these insights, significant mysteries remain about Saturn's internal structure, particularly regarding the exact composition and extent of its core and the precise mechanisms driving its magnetic field. But the internal mysteries are only part of the story. What truly makes Saturn unlike any other planet in our solar system is not what lies beneath the clouds, but what orbits around it. The rings. They are there, visible, monumental, impossible to ignore. And yet they represent one of the most puzzling features in the entire solar system. How did they get there? What are they made of? How do they persist when every known law of physics suggests they should have collapsed, dissipated, or collided themselves into oblivion billions of years ago? These are not rhetorical questions. They are genuine puzzles that have driven planetary scientists into decades of research, speculation, and careful observation. For thousands of years, the rings remained invisible to human eyes, hidden beyond the resolving power of naked sight. The first telescope observations in the early 1600s revealed something impossible, something that should not have been there, something that contradicted every assumption about what a planet could be. When Galileo saw Saturn through his primitive telescope, he did not understand what he was looking at. His instrument was not powerful enough, not clear enough, to resolve the rings into what they actually were. He saw appendages, strange handles, companions to the planet. Other observers reported different interpretations. The rings were confusing, contradictory, utterly mysterious. It was not until much later that astronomers realized what they were actually observing. And by then, a new mystery had already taken root in the soil of scientific curiosity. Why would a planet have rings? What physical process could create such a structure? What kept the rings from collapsing inward or flying apart into space? These questions had no answers in classical physics. The mathematics seemed to suggest that rings should not be possible, that gravity should pull them inward or allow them to escape. Yet there they were, undeniably real, stubbornly existing in defiance of theoretical expectations. By the time telescopes became powerful enough to reveal the true nature of Saturn's rings, more questions had accumulated than answers. There were multiple rings, not just one. They had gaps and divisions. They exhibited waves and ripples as if something was shaping them. Ring spokes appeared and disappeared on timescales of hours. The rings exhibited structure, organization, dynamic processes. This was not some static, ancient feature of Saturn. This was something alive, in the sense that geologically active systems are alive. The rings were changing, evolving, responding to forces and influences still not fully understood. Throughout the 19th and 20th centuries, astronomers carefully studied Saturn and its rings. Spectroscopy revealed the composition. They were made of ice, primarily water ice, small particles reflecting light, organized into bands. But why would ice particles maintain such perfect orbits? Why would they not collide and stick together? Why would some rings be dense, while others were nearly transparent? Why were there gaps? What created the gaps? What maintained them against the natural tendency of particles to drift and diffuse? Photography improved. Telescopes grew more sophisticated. Spectroscopy advanced. Yet the mysteries only deepened. The rings seemed to demand explanation, but resisted it at every turn. By the time space probes were launched toward the outer solar system, Saturn's rings had become one of the great unsolved puzzles in planetary science. They were visible, measurable, observable, and yet fundamentally mysterious. The rings did not behave as theory predicted they should. They seemed to possess properties and characteristics that required explanation, yet the explanations remained incomplete. When the Voyager spacecraft reached Saturn in the 1980s, it sent back images that revolutionized our understanding of the rings, while simultaneously raising more questions. The rings were far more complex than anyone had imagined. There were not dozens of rings, but thousands, perhaps hundreds of thousands. Fine structure became visible through the Voyager cameras. Density waves rippled through the rings. The Cassini orbiter, which arrived in 2004 and remained in the Saturn system until 2017, provided even more detailed information. For 13 years, Cassini orbited Saturn repeatedly, diving between the rings and the planet, measuring particle properties, analyzing composition, tracking dynamics. Every pass revealed new details, new mysteries, new questions that demanded answers. The wealth of information that Cassini provided has kept planetary scientists busy for years. Data continues to be analyzed and reanalyzed. New discoveries continue to emerge from careful examination of the measurements and images that Cassini collected. Yet, despite all this observation, despite decades of study, despite spacecraft missions and mathematical models and computer simulations, Saturn's rings remain among the most mysterious objects in the solar system. They are visible, well-studied, thoroughly photographed, and yet we do not fully understand them. The rings are real. They are there. We can measure them, observe them, calculate their properties. We know they orbit Saturn, that they are made of ice and rock, that they extend outward for many hundreds of thousands of kilometers. We know there are multiple rings with different properties and characteristics. We know the rings are thin, incredibly thin, a feature almost incomprehensible in its extremity. The rings extend outward from Saturn for about 175,000 miles, a distance greater than the distance from Earth to the Moon. Yet their vertical thickness is only about 30 feet, or roughly 10 meters in the main rings. If you were to create a scale model of Saturn's rings the size of a football field, the rings would be thinner than a single sheet of paper. This extreme thinness is one of the most remarkable characteristics of the ring system. How can something so thin maintain itself against the constant tidal forces pulling at it? How can gravity organize particles into such a geometrically precise, extremely flat configuration? The rings should collapse. The mathematics suggests collapse. The physics predicts collapse. Yet they do not collapse. They persist, organized, structured, visible. The rings are composed primarily of water ice particles. Cassini's instruments analyze the light reflected from ring particles and determine their composition with remarkable precision. Water ice dominates, the same crystalline ice that forms glaciers on Earth and polar ice caps. This ice is contaminated by other materials, dust and rocky compounds that darken the ice and alter its reflectivity. But the primary component is water ice. Billions upon billions of particles ranging in size from dust grains smaller than snowflakes to chunks as large as houses. Some estimates suggest particles as large as mountains exist within the ring system. These particles do not stay still. They orbit Saturn, moving in paths determined by gravity and orbital mechanics. The orbital velocity of ring particles increases closer to Saturn and decreases farther out, exactly as orbital mechanics predicts. A particle at the inner edge of the main rings moves faster than a particle at the outer edge. This difference in velocity is crucial to understanding ring structure and behavior. Where particles move at the same velocity, they maintain stable orbits together, forming dense rings. Where velocity differences create shear forces, structure emerges. Waves form in the ring particles as they respond to gravitational perturbations. The rings are not passive structures. They are dynamic systems, responding to forces and influences. The discovery of ring waves was revolutionary. It meant that something was shaping the rings. Something was causing organized patterns to emerge. Scientists eventually realized that the moons of Saturn play crucial roles in ring rupture. A moon orbiting just outside a ring gap creates gravitational perturbations that maintain the gap against the natural tendency of particles to drift inward. A moon orbiting within a ring can clear a path for itself, creating a division. Moons orbiting close to the rings generate waves by their gravitational influence. Waves ripple outward through the rings, patterns of density variation that propagate over time. These waves can be incredibly subtle, barely perceptible in casual observation, yet they carry information about the masses of the moons that generate them. By studying the waves in Saturn's rings, astronomers can determine the masses of moons that might be too small to see directly. This is one of the profound insights that ring science has provided. The rings are not just structures of interest in themselves. They are also tools for learning about Saturn's moon system. The rings reflect the gravitational influence of the moons. The rings encode information about mass distribution, orbital positions, orbital resonances. Read correctly, the rings become a kind of record, a geological narrative written in particle distributions and density waves. But the rings reveal mysteries at smaller scales as well. There are features in the rings that appear and disappear with remarkable rapidity. The most famous of these are ring spokes, dark or bright linear features that extend radially across the rings. These spokes appear, last for a few hours or days, and then fade away. They rotate almost synchronously with Saturn's magnetosphere, not with the rings themselves. This is bizarre. Something in the magnetosphere seems to be organizing dust particles into linear patterns that persist for hours. What mechanism could do this? Scientists have proposed several theories. Electrostatic forces could suspend dust particles, allowing them to organize into linear patterns. Small meteoroid impacts could release dust particles that then respond to electromagnetic forces. Lightning in Saturn's atmosphere could generate electron beams that organize dust particles. But none of these theories has been proven definitively. The ring spokes remain mysterious, appearing and vanishing, responding to forces still not fully understood. The spokes are ephemeral, transient, vanishing as quickly as they appear, yet they demonstrate that the rings are not static. Something is happening within the rings. Something is organizing, shaping, influencing. The rings are not simply a collection of particles in stable orbits. They are a dynamic system responding to multiple forces simultaneously. There are also mysterious variations in ring brightness and color. Some regions of the rings are darker, absorbing more light. Other regions are brighter, more reflective. These variatio, ENS, suggest differences in composition or particle size distribution. The darker material might represent contamination from meteoroid impacts or chemical alteration from exposure to radiation. The brighter material might represent relatively fresh ice particles that have not yet been altered by exposure to the solar environment. But the exact mechanisms creating these variations remain incompletely understood. As more data has accumulated from spacecraft observations, the picture of ring composition has become increasingly complex. The rings are not simply water ice. There are organic compounds present. There are rocky materials mixed with the ice. There may be salts or other compounds incorporated into the ice particles. The chemical composition varies from region to region within the RNA G system. Some rings are nearly pure water ice. Others contain significant fractions of rocky material. The origin of this compositional variation is not entirely clear. It may reflect different formation mechanisms. It may reflect different ages of material. It may reflect chemical alteration processes occurring at different rates in different ring regions. The fundamental mystery of why rings would exist at all remains central to ring science. In principle, gravity and orbital mechanics suggest that in a system as massive as Saturn surrounded by moons and other objects, collisions should accumulate and eventually lead to the formation of a single large moon rather than a persistent ring system. Yet Saturn's rings persist. They have not coalesced into a moon. They have not dissipated into space. They have not collided with Saturn. They exist as a stable, or at least long-lived, configuration of billions of particles organized into multiple rings. What keeps them organized? What maintains their structure against the forces that should disrupt them? The answer involves the gravitational influence of Saturn's moons. Moons orbiting within and around the ring system create gravitational patterns that organize the rings and maintain their structure. A moon orbiting just outside a ring can launch gravity waves that propagate through the ring, creating organized structure. A moon can create a gap in a ring by gravitationally clearing a path for itself. Smaller moonlets, some too small to see in casual observation, but detectable through their gravitational effects on rings, can shepherd ring particles into organized lanes or patterns. The rings and the moons are intimately connected. The rings exist because of the moons. The ring structure reveals the presence and masses of the moons. The rings and moons interact gravitationally, mutually influencing each other. Saturn's ring system is not simply a collection of particles. It is a system in which gravity and orbital mechanics have organized material into a configuration of remarkable stability and structure. Understanding how this system works requires understanding orbital resonances, tidal forces, density wave propagation, and the complex gravitational interactions between rings and moons. This is the realm where modern ring science operates. Yet despite all this understanding, questions remain. Why is Saturn surrounded by such magnificent rings when other planets have rings that are comparatively faint or less extensive? Why does Saturn's ring system have such a distinctive structure of multiple rings with gaps and divisions? Why are some of Saturn's moons relatively spherical while others are elongated or have unusual shapes? Why does one moon, Iapetus, have an equatorial ridge that makes it look like a walnut? These are not trivial questions. They connect to fundamental issues about how planetary systems form and evolve. The ring system of Saturn appears to have a history, a narrative of change and transformation. It was not always as it appears now. Something happened. Something shaped it. Something determined its current structure. What was that something? The answer has become one of the major questions in planetary science. For most of the 20th century, scientists assumed that Saturn's rings were ancient, perhaps nearly as old as Saturn itself, having formed in the primordial disk of material from which Saturn accreted. They assumed the rings had persisted essentially unchanged for billions of years, stable features of Saturn's system since the early solar system. This assumption made intuitive sense. If rings had persisted for billions of years, they must be stable. If they were stable, they must have been there since the beginning. But in the early 2000s, new observations and theoretical models began to suggest something radically different. The Cassini spacecraft's detailed measurements of the rings and Saturn's gravitational field provided data that contradicted the ancient rings hypothesis. The rings appeared to be much younger than expected. Some models suggested the rings were only a few 100 million years old. Others suggested they might be even younger, perhaps only 100 million years old. This was shocking. Saturn's rings might not be ancient witnesses to the early solar system. They might be relatively recent features, young features, perhaps even features that formed during the era when dinosaurs roamed the Earth. If the rings were truly so young, something must have happened to create them. Something must have disrupted Saturn's system dramatically enough to generate the rings. What could that something have been? This is where the great ring formation theories emerge. Some scientists proposed that a large moon had been destroyed. Perhaps a collision between two moons had shattered one of them, generating the debris that became Saturn's rings. Perhaps a moon had strayed too close to Saturn and been torn apart by tidal forces, with the fragments spreading outward to become the rings. Perhaps Saturn had captured a moon from elsewhere, and this captured moon had collided with another body, scattering material that became the rings. Each of these mechanisms could potentially create a ring system. But which one actually happened? The evidence is fragmentary, incomplete, suggestive, but not definitive. Multiple theories compete for acceptance. The ring formation mystery remains one of the great outstanding questions in planetary science. Whatever process created the rings, whether it happened billions of years ago or more, recently, the rings now exist as a visible, measurable, observable feature of Saturn. They are there, orbiting silently, maintained by gravity and orbital mechanics, slowly radiating away the energy they possess. Recent Cassini observations revealed something unexpected about the rings. They are not permanent. Material from the rings is falling into Saturn's atmosphere. Thousands of kilograms of ice per second are raining down into Saturn, falling from the rings onto the planet below. If this process continues at the current rate, the rings could be completely gone within a few 100 million years. The magnificent rings that we observe today, the rings that make Saturn unique among planets, might be temporary. They might be features destined to vanish. In the vast cosmic timescale, the rings might be ephemeral, here for only a moment, here during our time in this universe, but absent in the distant future. This realization has prompted a fundamental reconsideration of Saturn's ring system. If the rings are young and if they are disappearing, then Saturn is in the middle of a ring epoch. The planet is experiencing a phase of its history when rings dominate its appearance. Eventually this phase will end. Eventually the rings will be gone. How many epochs has Saturn experienced? Has Saturn had rings before? If the rings are disappearing now, might they be replaced by new rings at some point in the future? These questions move into the realm of speculation, beyond what current observations can answer. But they illustrate the profound shift in how scientists understand Saturn's rings. The rings are not eternal monuments. They are features of a moment, important and remarkable, but ultimately temporary. The detailed structure of Saturn's rings, as revealed by Cassini and earlier spacecraft, presents a landscape almost incomprehensible in its complexity. The primary ring system consists of multiple distinct rings, each with its own characteristics, each responding to different gravitational influences. The A ring, the B ring, and the C ring are the most prominent, the most visible, the most easily observed from Earth-based telescopes. But these primary rings are surrounded and subdivided by fainter rings, intermediate rings, dusty rings that contain smaller particles than the main rings. There are gaps within rings, divisions that separate different regions, structures that reflect the gravitational influence of moons. Some of these gaps and divisions are large enough to see easily. Others are subtle features, barely perceptible in casual observation, but clearly visible in high-resolution spacecraft images. Each gap tells a story about gravitational interactions. Each division suggests the presence of a moon or moonlet, creating a gravitational pattern that organizes ring particles into distinct regions. The total mass of Saturn's rings is estimated to be equivalent to the mass of the moon Enceladus, one of Saturn's notable moons. This means the rings contain a tremendous amount of material, billions of tons of ice and rock spread across an area the size of a planetary disk. Yet this material is distributed so thinly that the rings are nearly transparent. You could see through them. Starlight penetrates the rings. The density of particles is low enough that collisions between individual particles are rare. The rings feel sparse, despite their impressive visual appearance. But within this sparseness, structure persists. Organization is evident. Patterns are clear. Waves ripple through the rings. Density variations follow mathematical patterns. The spokes appear and disappear. All of this organization suggests that forces are at work, forces that we have only partially understood. One of the most mysterious ring features are the enigmatic spokes that appear in Saturn's rings, particularly in the B ring. These dark linear features extend radially from Saturn outward through the rings, sometimes spanning thousands of kilometers in length. They appear suddenly, last for hours or a day or two, then fade away mysteriously. What is strange about the spokes is that they rotate with Saturn's magnetosphere, not with the rings themselves. Particles at different distances from Saturn orbit at different speeds, yet the spokes rotate synchronously with something in Saturn's magnetosphere. How can invisible electromagnetic fields organize visible dust particles in the rings into linear patterns? The leading hypothesis suggests spokes consist of microscopic dust particles suspended by electrostatic repulsion. Charged particles exposed to UV radiation repel each other electrostatically, lifting slightly above the ring plane. The magnetosphere rotates with Saturn's deep interior, creating an electromagnetic pattern. If the magnetosphere has structure with varying electrical field strength, these regions would exert different forces on charged particles, organizing them into the linear patterns we observe as spokes. The spokes appear and disappear because underlying magnetospheric conditions vary. The spokes are ephemeral manifestations of deeper electromagnetic phenomena. Yet this explanation remains incomplete. The exact mechanism of spoke formation remains unclear, and the phenomenon requires more observation and analysis. Beyond the prominent rings and the mysterious spokes, there are fainter ring features that pose their own puzzles. The G ring, for example, is a faint dusty ring that appears to be maintained by a collision process between larger icy particles and micrometeoroid impacts. The G ring seems to be produced by relatively large icy particles confined within a bright arc on the ring's inner edge. These particles are held in place by gravitational effects from Saturn's moon Mimas. Micrometeorites collide with these larger particles at regular intervals, knocking off dust-sized fragments. Plasma from Saturn's magnetosphere sweeps through the ring, dragging these fine particles outward and scattering them. This creates a steady state where dust is continuously being produced by impacts and continuously being removed by magnetospheric plasma. The result is the observable G ring. a faint dusty feature that persists because of a constant cycle of destruction and replenishment. The G-ring demonstrates that Saturn's rings are not simply collections of primordial material sitting in stable orbits. They are dynamic systems where processes are occurring, where material is being created and destroyed, where interactions between different components of Saturn's system are constantly reshaping the rings. The discovery of the G-ring and understanding of its maintenance mechanisms illustrate the sophistication of ring science. Scientists must consider orbital mechanics, gravitational interactions between rings and moons, collisional processes, electromagnetic forces, and the flow of plasma through Saturn's magnetosphere. A complete understanding of Saturn's rings requires integrating all of these different physics domains into a coherent picture. Yet even as understanding has advanced, mysteries persist. There is still no complete, unified theory explaining all aspects of Saturn's ring system. Different rings require different explanations. Different features require different mechanisms. Some aspects of ring behavior remain poorly explained or not explained at all. The rings continue to surprise us, to present puzzles, to demand further investigation and deeper understanding. The question of why Saturn has rings, while other planets have only faint or non-existent ring systems, remains fundamentally mysterious. The Cassini mission showed that Jupiter, Uranus, and Neptune all have rings. Though Jupiter's rings are faint and dark, Uranus's rings are narrow and distinct, and Neptune's rings are fragmented and incomplete. None of these compare to Saturn's spectacular ring system. Why would Saturn accumulate or maintain such an extensive and visible system of rings while other gas giants do not? Some of this may relate to Saturn's distance from the Sun and its specific mass and orbital characteristics. Some may relate to the particular configuration of moons around Saturn and the gravitational dynamics they create. Saturn may simply have experienced the right conditions at the right time to create and maintain rings. Or Saturn may have acquired rings more recently through a collision event that other planets either did not experience or experienced differently. The exact reasons for Saturn's distinctive ring system remain unclear. What is clear is that Saturn's rings represent one of the most distinctive and visually spectacular features of our solar system. They have captured human imagination since the first glimpse through a telescope revealed their existence. They continue to surprise scientists with their complexity and their mysteries. They represent a realm of physics and astronomy that is still actively being investigated, still yielding new insights, still demanding deeper understanding. The rings are real, visible, accessible to study, yet they remain at the frontier of planetary science, presenting challenges that push our understanding of orbital mechanics, gravitational dynamics, and the nature of planetary systems themselves. One of the most profound discoveries from the Cassini spacecraft was the revelation that Saturn's rings are gradually disappearing. During its final orbits in 2016 and 2017, Cassini's instruments detected material falling from the rings into Saturn's upper atmosphere. The amount is substantial, approximately 10,000 kilograms of ice per second, a continuous rain of material descending from the rings into the planet below. This rate of material loss has profound implications. If the rings continue to lose material at this rate, they could be completely depleted within a few 100 million years. A few 100 million years sounds like an enormous time scale, but in the context of solar system evolution, where planets are billions of years old, it is not particularly long. The Sun will live for another 5 billion years or more. In that time, Saturn's rings could disappear multiple times over and be rebuilt and disappear again. But for the moment, for this epoch, the rings are here. They are visible, they are spectacular, but they are also temporary. This realization changes how we think about Saturn's rings. They are not ancient, unchanging monuments. They are temporary features of a particular era. The epoch of Saturn's rings is happening now in our time, during the era when humans exist and can observe them. In the distant future, perhaps in tens of millions of years, Saturn may appear very different from how it appears today. The rings may be gone, dissipated into Saturn's atmosphere. New rings might form if appropriate conditions arise. Or Saturn might continue as a ringed planet, but with a different ring configuration. The transience of Saturn's rings adds poignancy to their observation. They exist, they are there, they are real, but they will not last forever. This temporary nature makes them all the more worthy of study and observation. Every observation of Saturn's rings is, in a sense, documentation of a transitional phase in Saturn's history. The spacecraft missions to Saturn, particularly Cassini's 13-year orbital mission, have provided unprecedented detail about the rings, yet vast mysteries persist. The gravitational effects of the moons are not fully mapped. The composition variations across the rings are not completely understood. The processes that maintain ring structure against the forces that should disrupt them are still being investigated. The origin of the rings remains debated, with multiple competing theories. The mechanisms that will ultimately lead to the complete dissipation of the rings, beyond simply the rain of material into Saturn's atmosphere, are not fully characterized. All of these open questions mean that Saturn's rings remain an active frontier of planetary science. New observations, new theoretical models, new spacecraft missions in the future may provide the answers that current data cannot. But for now, the rings remain largely mysterious, visible but not fully understood, spectacular but in need of further investigation. The question of when Saturn's rings actually formed has proven to be one of the most contentious and fascinating debates in planetary science. For most of the 20th century, the consensus was clear. Saturn's rings were ancient, nearly as old as Saturn itself, perhaps having formed in the primordial solar nebula as part of Saturn's initial accumulation of material. This assumption made intuitive sense. Rings seemed like stable structures that would persist unchanged across billions of years. If they had persisted that long, they must have formed early. This ancient rings scenario was widely accepted without serious challenge until the early 21st century. But the detailed measurements from the Cassini spacecraft began to suggest something radically different. The gravitational measurements of Saturn and the rings revealed mass distributions that did not match expectations for ancient rings. The composition measurements showed properties that seemed inconsistent with 4 billion years of accumulated space weathering and chemical alteration. The orbital dynamics of Saturn's moons appeared to tell a story of relatively recent disruptions and reorganizations. All of these observations suggested that the rings might be far younger than previously believed. Some initial estimates placed the rings at only a few 100 million years old, meaning they would have formed sometime in the Mesozoic era, the age of dinosaurs on Earth. Other models suggested the rings could be even younger, perhaps only 100 million years old, or younger still. If this were true, Saturn would have experienced a dramatic event recently in geological terms, an event that created or exposed the rings. What could such an event have been? The leading theory involves the disruption or destruction of a large moon. Researchers proposed a concept called the lost moon Chrysalis, a moon that existed in Saturn's system perhaps 1 to 2 billion years ago. This moon, estimated to be roughly the size of Appendages, one of Saturn's current large moons, somehow experienced a catastrophic disruption. Perhaps it collided with another body. Perhaps it was disrupted by a close encounter with another moon. Perhaps it strayed too close to Saturn and was torn apart by tidal forces. Whatever the mechanism, most of this moon was accreted into Saturn itself, either falling directly into the planet or being absorbed through processes of gravitational consolidation. But a portion of the debris, perhaps 1% of the total mass, was ejected outward into orbit around Saturn, this debris spread out, organized by gravity and orbital mechanics, and became Saturn's rings as we observe them today. The theory elegantly explains why the rings are young, why their composition differs from older primordial material, and why Saturn's ring system is so distinctive and extensive compared to other planets. Yet not all scientists have accepted this theory. There remain proponents of the ancient rings hypothesis, those who argue that the Cassini data can be reinterpreted to support rings that are truly ancient, perhaps slightly younger than Saturn itself, but still billions of years old. The debate has become increasingly sophisticated and data-driven. Both sides marshal evidence and arguments. Both sides propose alternative explanations for data that seems to support the other position. The scientific discussion remains active and productive. This is how science should work, with competing hypotheses being tested against observations, with evidence being carefully evaluated, with competing teams of scientists arguing their positions and working to resolve the conflicts through new observations and deeper analysis. The resolution of the ring-age debate likely requires more data. Future spacecraft missions to Saturn might provide measurements that definitively settle the question. More detailed analysis of Cassini data might reveal details that have been overlooked. The theoretical models might explain observations in ways that change interpretations. Or the debate might persist, with both sides presenting credible arguments and observations that cannot be definitively reconciled with current information. The uncertainty about ring age exemplifies the frontier nature of planetary science. We observe, we measure, we analyze, and yet questions persist. The universe remains partly mysterious, partly knowable, partly waiting for future discoveries to illuminate what is currently obscure. Saturn's rings represent one of the most beautiful puzzles in that partially mysterious universe. They are there, visible, accessible to observation, yet still capable of surprising us, still demanding explanation, still inviting us to investigate further and to seek deeper understanding of how planetary systems form, evolve, and change across billions of years. But the rings, while spectacular and mysterious, represent only one part of Saturn's story. Beyond the rings, orbiting through the space around Saturn, lies another mystery that rivals the rings in complexity and significance. Saturn possesses a moon system of astonishing scale and variety, a miniature solar system within the Saturn system itself. As of recent counts, conducted in 2025, Saturn has at least 274 confirmed moons, with more discoveries happening regularly as astronomical technology improves and as more careful analysis of spacecraft data reveals previously unknown small satellites. This makes Saturn the champion of our solar system in terms of sheer moon quantity, surpassing Jupiter, which has approximately 95 known moons, GI, giving Saturn nearly 3 times as many known satellites as Jupiter. No other planet in our solar system comes close to Saturn's lunar abundance. These moons range dramatically in size from the enormous to the minuscule. Some are massive worlds, large enough to be called minor planets in their own right, with diameters exceeding 1,000 kilometers. Others are tiny, mere kilometers across, more akin to asteroids that happen to orbit Saturn rather than wandering freely through space as independent bodies. The largest, Titan, is a world unto itself, so substantial and complex that it deserves consideration as almost a planet orbiting another planet. A moon so large and so geologically complex that it rivals Earth in its diversity of environments and processes. The smallest moons are so diminutive that they barely hold together under their own gravity, their weak gravitational fields unable to pull them into perfectly spherical shapes, leaving them as irregular, potato-shaped bodies. What binds all these moons together in Saturn's system is gravity and orbital mechanics. They dance around Saturn in prescribed paths, determined by Newton's laws and Einstein's refinements to those laws. Their velocities and distances determined entirely by the laws of physics, each moon influencing the others through gravitational attraction. Some moons orbit in resonance with one another, their orbital periods related by simple ratios like 2:1 or 3:2, creating patterns of gravitational interaction that have evolved and been fine-tuned over billions of years. Other moons seem to orbit more independently, their paths influenced primarily by Saturn's gravity rather than by interaction with neighboring moons, their orbits determined by where they happen to be and their veloci. The sheer number of Saturn's moons and their diverse characteristics suggest a complex history of capture and collision. Some moons may have formed from Saturn's primordial disk of material during Saturn's formation billions of years ago. Others may have been captured from elsewhere, wandering asteroids drawn into Saturn's gravity well and incorporated into the system. The smaller moons might be fragments from collisions between larger bodies, debris scattered from impact events that occurred at various times in Saturn's history. Each moon's position in its orbit, its composition and physical characteristics, and its orbital properties tell a story about Saturn's history, if we can learn to read the signs correctly. Understanding Saturn's moon system requires grappling with fundamental questions about planetary formation and the accumulation of planetary systems, orbital evolution and how orbits change over time due to collisions and gravitational interactions, and the long-term stability of complex gravitational systems with many interacting bodies. Titan dominates Saturn's moon system, not just in size but in complexity and scientific interest. Titan is the second largest moon in the entire solar system, larger than the planet Mercury, though less massive because it contains far more water ice and less heavy rocky material. It is 48% larger in diameter than Earth's own moon and 80% more massive, making it a substantial world by any standard. Saturn's largest moon possesses characteristics so remarkable that it challenges our conventional understanding of what constitutes a moon versus a planetary body. Titan is the only moon in our solar system known to possess a substantial atmosphere. This atmosphere is denser than Earth's atmosphere at sea level, thicker and heavier, composed primarily of nitrogen with traces of methane and other organic compounds. The atmospheric pressure at Titan's surface is greater than Earth's, creating an environment that feels almost oppressively heavy by terrestrial standards. The atmosphere creates a dense, impenetrable haze that renders Titan's surface completely invisible to telescopes looking through ordinary visible light. You cannot see Titan's surface from orbit without special instrumentation. The orange-colored haze that appears in images of Titan is created by complex organic molecules called tholins, produced when ultraviolet radiation from the distant sun interacts with atmospheric methane and nitrogen. This haze is responsible for Titan's distinctive appearance and also conceals the surface from casual observation. The Cassini spacecraft, which orbited Saturn for 13 years from 2004 to 2017, employed sophisticated radar and infrared imaging to pierce through Titan's atmospheric veil and reveal what lay beneath. Radar can penetrate through atmospheric haze to image the surface directly. Infrared imaging allows detection of radiation emitted from or reflected by the surface at wavelengths that pass through the haze. What these instruments discovered was a landscape almost shockingly familiar, almost Earth-like in its diversity and complexity, a world that looks more like home than any other place we have found beyond Earth. Titan possesses rivers, not of water, but of liquid methane and ethane. These hydrocarbon rivers flow from highlands to lowlands, carving channels and valleys through Titan's terrain, much as water shapes landscapes on Earth. The river valleys are visible in radar images as branching patterns suggesting flowing liquid over extended periods. Liquid methane and ethane are not water, but they serve strikingly similar roles in Titan's hydrological cycle. They evaporate from the surface during warmer periods, form clouds in the atmosphere through condensation of vapor, fall as rain on the surface, and flow across the landscape toward lowlands and seas. The chemistry is entirely different from Earth's water cycle, but the fundamental process is strikingly similar, suggesting that liquid cycles are a general feature of planetary systems where conditions allow volatiles to exist in multiple phases. Titan also possesses lakes and seas. These are not small bodies of water, but substantial accumulations of liquid hydrocarbons, large enough to be considered inland seas. The largest, Kraken Mare, is larger than Earth's Caspian Sea, one of the largest bodies of water on Earth. There are also smaller lakes and seas scattered across Titan's polar regions, with concentrations particularly notable at the North Pole. These bodies of liquid represent something almost incomprehensible to inhabitants of Earth accustomed to water. Imagine vast seas of liquid with properties similar to gasoline or paint thinner, pools of organic compounds that would ignite explosively and violently if exposed to free oxygen. Yet on Titan, beneath a nitrogen atmosphere, at temperatures of -178 to -94 degrees Celsius, depending on latitude and season, these liquids remain perfectly stable and inert. They do not evaporate rapidly. They do not degrade chemically. They persist as ocean-like bodies, creating an alien hydrosphere as strange and fascinating as anything science fiction has imagined, yet entirely real and measurable and documented by spacecraft instruments. Titan's surface also exhibits vast deserts of hydrocarbon sand dunes. These dunes cover significant portions of Titan's equatorial regions, suggesting wind-driven processes that move sand-sized particles across the surface over extended time scales. The winds at Titan's surface are much slower than the winds in the upper atmosphere, but they are sufficient to move fine particles and organize them into dune patterns. The dunes themselves are composed not of silicate sand as on Earth, but of complex organic compounds produced by the interaction of sunlight with atmospheric methane and other molecules. The dunes represent the accumulated product of billions of years of complex atmospheric chemistry occurring high in Titan's atmosphere, with chemical reactions being driven by ultraviolet radiation from the sun and cosmic rays, producing increasingly complex organic molecules that eventually condense and settle downward, falling as dark organic particles onto the surface. The dunes represent a kind of atmospheric sediment, the fallout from chemical processes occurring in the sky above. Beyond lakes and dunes and rivers, Titan harbors another secret that has only recently been confirmed through careful analysis of Cassini's gravity measurements. Beneath Titan's surface lies an ocean of liquid water, mixed with salts and possibly ammonia, forming a layer that may be hundreds of kilometers thick, potentially thicker than all the oceans of Earth combined. This subsurface ocean represents a completely different environment from the surface methane lakes. While the surface is cold by Earth standards, but wet with liquid hydrocarbons at temperatures where methane and ethane can flow like water, the subsurface is frozen in the icy crust above, but liquid with warm water in the depths below. The ocean is separated from the surface by a layer of water ice hundreds of meters thick or possibly thicker, creating a barrier between the two worlds. Titan thus presents not one, but two completely different potential habitats. One surface environment with methane lakes and rainfall, one subsurface environment with water and potentially geothermal heat, each with its own chemistry, its own temperature regime, its own possibility for harboring exotic forms of life that we can barely imagine. Scientists have proposed that Titan's subsurface ocean might contain complex chemistry at the boundary between rock and water, where heat from Titan's interior could drive chemical reactions that produce energy. On Earth, Such environments, deep in the ocean floor near hydrothermal vents, harbour thriving communities of organisms that require no sunlight and instead derive energy from chemical gradients created by geological processes. These organisms use chemosynthesis rather than photosynthesis, extracting energy from reactions between hot, mineral, rich water emerging from the planet's interior and cold seawater above. Might Titan harbour similar life in its subsurface ocean? Might there be organisms in Titan's water ocean using similar chemistry to gain energy and sustain life? The question remains unanswered, but it is a question worth asking, a mystery worth investigating. The existence of Titan's subsurface ocean, combined with evidence of geothermal activity and complex organic chemistry in Titan's atmosphere, makes Titan perhaps the most scientifically intriguing location in the solar system for the search for life beyond Earth. Future missions are being planned to land on Titan and directly investigate its surface environment. The Dragonfly mission, scheduled to arrive at Titan in the 3030s, will deploy rotorcraft to explore multiple sites on Titan's surface, collecting samples and searching for signs of chemical processes that might indicate ether. Titan's atmosphere presents mysteries as profound as its surface and subsurface worlds. The methane that dominates Titan's volatile chemistry is continuously being broken down by ultraviolet radiation from the distant sun. This photochemical destruction process is well understood. Methane molecules are struck by photons and split into smaller fragments. These fragments recombine to form other molecules, including complex organic compounds. But the original methane is lost in the process. The rate of methane destruction in Titan's atmosphere can be calculated from first principles and from observations. The calculations suggest that all of Titan's atmospheric methane should be completely depleted over a period of only a few million years, a very short timescale in geological terms. Yet Titan possesses a substantial atmosphere rich in methane. The atmosphere has persisted for billions of years. Something must be continuously replenishing methane to balance the loss. Where does this methane come from? One possibility is cryovolcanism. Volcanoes that erupt not molten rock, but slurries of ice and water, or ice and methane. If Titan's interior is warm enough to drive such eruptions, methane could be released from subsurface reservoirs onto the surface and into the atmosphere, providing the replenishment needed to maintain the atmospheric methane inventory. But is Titan warm enough for cryovolcanism? The evidence remains inconclusive. Titan is heated by tidal friction from Saturn's gravity, but whether this heating is sufficient to melt ice and drive eruptions is debated. Another possibility is that methane is being released from Titan's surface or interior through non-volcanic processes, perhaps from decomposition of complex organic material produced by atmospheric chemistry, or from outgassing of frozen methane clathrates, ice structures that contain methane trapped in their crystalline matrix and can release methane if heated or depressurized. A third possibility is biological origin. Methane produced by microorganisms if life exists on Titan, though this remains entirely speculative. The answer remains unknown, and the mystery of Titan's methane source remains one of the great puzzles in planetary science, one that will require future observations to definitively resolve. Titan's atmosphere also contains complex organic compounds far more intricate than simple methane. Scientists have detected propylene, a chemical with 3 carbon atoms and implications for increasingly complex chemistry. They have found cyanide, a compound that plays important roles in prebiotic chemistry on Earth, the chemistry that exists before life emerges, but that provides building blocks for life. Hydrogen cyanide, another cyanide compound, has also been detected. These discoveries suggest that Titan's atmosphere is undergoing complex photochemistry, reactions driven by ultraviolet radiation from the sun that produce increasingly complex organic molecules from simpler building blocks. Starting with methane and nitrogen, the simplest molecules, photochemical reactions create amino acids, nucleotide precursors, and other compounds associated with life on Earth. Given enough time, given the right conditions, might such chemistry eventually produce life? Or might it produce only complex organic compounds forever trapped in the cold titanian atmosphere, never assembling into anything we would recognize as alive? Or might it produce life of an entirely different character, based on completely different chemistry than life on Earth? The question is fascinating, not because we know the answer, but because we do not. And the only way to answer it is to investigate Titan thoroughly. Titan's formation adds another layer of mystery to this already enigmatic world. Recent research suggests that Titan might have acquired its current mass and configuration through a collision event early in Saturn's history. This theory proposes that a massive moon, perhaps 500 million years ago, collided with the proto-Titan, merging with it and fundamentally altering its properties. This collision, if it occurred, might have also triggered a cascade of gravitational disruptions that affected other moons in Saturn's system, potentially contributing to the formation of Saturn's rings themselves. The theory links Titan, the rings, and Saturn's unusual axial tilt into a single catastrophic event, suggesting that Saturn's most distinctive features might all be consequences of a single ancient collision. If true, this would mean that Saturn, as we observe it today, is still bearing the scars and the consequences of events that occurred hundreds of millions of years ago. The moon system remembers. The rings remember. The planet's orientation remembers. History is written in the structure of the Saturn system for those with the knowledge to read it. Enceladus, another of Saturn's major moons, represents a different kind of mystery, smaller than Titan, but in many ways more surprising in its geological activity. Enceladus is a relatively small moon, only about 500 kilometers in diameter, comparable in size to a large terrestrial state or a small country. Yet it possesses characteristics that have made it one of the most scientifically interesting bodies in the solar system. The surface of Enceladus is covered with water ice, as expected for a moon orbiting in Saturn's system at a distance where temperatures are so cold that water remains solid as rock-hard ice. But the ice is not uniform across the moon. In the southern polar region, the ice is heavily fractured and broken, scarred by long cracks and ridges extending across the landscape. These cracks do not appear to be ancient features slowly modified over billions of years by cosmic ray damage and space weathering. They appear fresh, with sharp edges and recent appearance, suggesting active processes occurring on Enceladus in the present day. And indeed, when Cassini flew past Enceladus multiple times during its mission, the spacecraft's instruments detected that these cracks are the sites of active geyser. Water vapor and ice particles erupt from beneath Enceladus's frozen surface, fountaining upward into space and creating a plume that extends thousands of kilometers above the surface into space. The geysers are not random or chaotic. They occur at specific locations along the southern polar cracks, suggesting that liquid water exists beneath the surface and is being heated by some process sufficiently to create the pressure needed to force water upward through cracks in the ice. The temperature in the geyser plume is warmer than would be expected from a cold surface, indicating heat coming from the interior. The geysers are not a transient phenomenon that appeared briefly and then ceased. They persist over years and decades, suggesting a stable source of liquid water and energy beneath the surface, not a temporary condition. Analysis of the geyser material collected by Cassini reveals the presence of organic compounds, salt water, with an ionic composition similar to Earth's oceans, silicon dioxide grains, and other components, suggesting that Enceladus harbors a subsurface ocean of liquid water, analogous to Titan's subsurface ocean, but fundamentally different in that this ocean is water, not methane, creating an environment more directly comparable to the oceans of Earth. The implications are staggering. Enceladus is small, only about 500 kilometers across. By the laws of planetary physics, small bodies should cool rapidly after their formation. Radioactive decay in their interiors provides a heat source initially, but as the radioactive elements decay and disappear, heat generation decreases. A moon the size of Enceladus should have cooled completely billions of years ago. Its interior solidified. All geological activity ceased. Yet Enceladus displays persistent heat and liquid water. How can this be? The answer appears to involve tidal heating, a phenomenon where gravitational forces generate heat within a body. Enceladus orbits within Saturn's gravitational field and is gravitationally perturbed by other moons, particularly the nearby moon, Dione. These gravitational perturbations prevent Enceladus's orbit from becoming perfectly circular. Instead, Enceladus's orbit is slightly elliptical, meaning the moon's distance from Saturn varies slightly as it moves through its orbit. As Enceladus moves in its elliptical orbit, it experiences varying amounts of gravitational stress from Saturn. When Enceladus is closest to Saturn, it experiences stronger gravitational pull. When it is farthest from Saturn, the pull is slightly weaker. This varying stress deforms the moon slightly, stretching and compressing it as it orbits. The stretching and compression causes friction within the moon's interior, as different layers of rock and ice flex and move relative to one another. This friction generates heat, converting the mechanical energy of orbital motion into thermal energy. The process is subtle, but over billions of years, tidal friction has accumulated enough heat to keep water liquid beneath Enceladus's surface, enough heat to drive the geysers, enough heat to potentially support life. It is a remarkable process. A small moon powered by the gravitational dance it performs with its parent planet and neighboring moons. The gravitational choreography of orbital mechanics converted into heat through the relentless friction of tidal flexing. This tidal heating has profound implications for the question of life. If Enceladus harbors an ocean of water with energy sources and organic compounds, it might be capable of supporting life, including microbial life, similar to extremophile organisms found on Earth in similarly extreme environments. The geysers themselves present an opportunity for exploration unlike anything available elsewhere in the solar system. A future spacecraft could fly through the geyser plume and sample the water and organic compounds directly, collecting material that has been ejected from Enceladus's subsurface ocean, potentially detecting signs of life if life exists on Enceladus. The ocean is hidden beneath hundreds of meters of solid ice, inaccessible to direct observation. But the geysers expose the ocean's composition to space and provide samples that can be collected and analyzed. Enceladus thus represents perhaps the most accessible location in the solar system where we might find evidence of life beyond Earth, where future spacecraft might return samples containing actual microbial life or biosignatures indicating past or present biological activity. Saturn's moon system contains many other worlds of interest beyond Titan and Enceladus, each contributing to our understanding of Saturn's complex system. Iapetus, the third largest moon by mass, possesses an unusual characteristic that makes it distinctive and somewhat mysterious among Saturn's satellites. Iapetus has an equatorial ridge, a mountain range that runs along its equator like a spine running down the back of a creature, making the moon resemble a walnut as viewed from certain angles. The ridge is not a small or subtle feature. It rises approximately 20 kilometers above the surrounding terrain and runs for thousands of kilometers around the moon's equator. This is an enormous structure, more prominent relative to the Moon's size than any mountain range on Earth relative to Earth's radius. How such a ridge formed is not entirely clear and remains a subject of ongoing debate. Various theories have been proposed involving collision with a large object, accretion of material in the equatorial region during formation, or tidal forces from Saturn stretching and reshaping the Moon early in its history. But no consensus has emerged among planetary scientists about which mechanism is correct. Iapetus is also characterized by dramatic color variations between hemispheres, with one hemisphere much darker than the other. The cause of this color difference remains incompletely understood, though observations suggest the darker material is concentrated on the leading hemisphere as Iapetus orbits Saturn. Some researchers propose that dust from other moons is being transferred to Iapetus through collisions or impacts, gradually darkening one hemisphere as material accumulates on the side facing the direction of orbital motion. Others suggest that the color difference results from internal processes bringing darker material to the surface, or from chemical changes occurring in surface material exposed to different levels of radiation on different hemispheres. Mimas, a small moon with a diameter of only 396 kilometers, is famous for its enormous impact crater dominating its surface. The CR Eta, named Herschel, is so large relative to the Moon's size that the impact nearly shattered the Moon entirely, perhaps coming close to the limit of what the Moon's internal strength could withstand before fragmenting. The crater's resemblance to the fictional Death Star from Star Wars has made Mimas recognizable to the general public and a favorite subject for popular science writers. But the scientific interest lies far beyond the popular culture reference. The crater itself, and what it reveals about the violent history of Saturn's moon system, is profoundly important. The existence of such an enormous impact crater on such a small moon suggests that Mimas experienced a collision event with another object traveling at tremendous speed, releasing energy equivalent to millions of nuclear weapons. The fact that Mimas survived the impact, rather than being shattered into fragments that would subsequently reaccrete into a moon of different shape, suggests something important about the moon's internal structure and composition, possibly indicating a stronger, more rigid interior than would be expected for an icy moon. The full implications of Mimas's survival of such a catastrophic impact remain subjects of ongoing investigation and theoretical modeling. Other moons, including Rhea, Saturn's second largest moon, and Dione, Tethys, and smaller bodies, present their own characteristics and mysteries. Rhea displays an unusual, possibly tenuous ring system discovered by the Cassini spacecraft, the first known moon to possess its own rings. Some show evidence of past geological activity, including cryovolcanic activity, where water ice mixtures erupted from the interior. Others display unusual surface features, including linear scarps and ridge systems, suggesting diverse formation histories and subsequent evolution through impacts, internal heating, or gravitational interactions with Saturn. Each moon in Saturn's system represents a world with its own history, its own geology, its own story to tell about the formation and evolution of the solar system, contributing pieces to the larger puzzle of understanding how planetary systems develop and change over billions of years. Saturn's atmosphere deserves consideration as more than just the backdrop for the rings and moons. The atmosphere itself is a place of remarkable phenomena and extreme conditions, a dynamic environment where physics operates at scales and intensities difficult to imagine from an Earth perspective. Saturn's atmosphere is composed primarily of hydrogen and helium, with traces of other compounds including methane, ammonia, and water vapor, plus various organic compounds produced by atmospheric chemistry. The atmosphere is arranged in distinct bands of clouds that circle the planet parallel to the equator. These bands are not static or unchanging. They flow at different velocities, creating wind patterns of extraordinary complexity and intensity. The fastest winds in Saturn's atmosphere reach speeds of approximately 1,800 kilometers per hour, or approximately 1,100 miles per hour, faster than any winds found in Jupiter's atmosphere, despite Jupiter's greater size and gravitational field, faster than any wind speeds measured anywhere else in the solar system, including the strongest hurricanes and tornadoes on Earth. These powerful winds do not represent temporary weather events. They are persistent features of Saturn's atmosphere, persisting over decades of observation. These winds are not driven primarily by energy from the Sun. Saturn is so distant from the Sun, approximately 10 times farther than Earth, that solar heating is minimal, contributing less than a few % of the energy driving atmospheric circulation. Instead, Saturn's winds are driven by the planet's internal heat. Heat from deep within Saturn's interior rises through the atmosphere, and this heat, as calculated and confirmed by multiple missions, provides the energy driving the wind patterns. This is fundamentally different from weather on Earth, where solar heating at the equator and cooling at the poles creates temperature gradients that drive wind patterns through differential heating and convection. On Saturn, internal heat provides the dominant source of energy for atmospheric circulation, making Saturn's weather fundamentally a product of the planet's internal engine rather than external solar forcing. The driving mechanism for Saturn's winds involves convection, the process by which heated fluid rises and cooler fluid sinks, creating circulation patterns of rising and sinking air. In Saturn's case, the fluid is the atmosphere itself, composed primarily of hydrogen and helium, rather than nitrogen and oxygen, and the heat comes from the planet's interior. Water vapor and other gases and condensed cloud particles heated from below rise upward, move poleward, lose heat to space through radiation, and sink back down toward the equator. This circulation pattern is complicated by Saturn's rapid rotation, with the planet completing a rotation once every 10 hours and 33 minutes, which deflects moving air into curved paths through the Coriolis effect, creating the banded structure we observe in the cloud patterns. The atmospheric bands persist year after year, decade after decade, century after century, suggesting stable, deeply established patterns of atmospheric circulation. Yet the details of how these patterns form and persist remain incompletely understood, particularly the question of why the bands have such specific latitudes and widths. Within Saturn's atmosphere, the famous hexagonal storm at the North Pole stands out as perhaps the most geometrically perfect feature in the entire solar system. This storm, discovered by the Voyager spacecraft in the 1980s when the probe flew past Saturn, has continued to spin for decades through the present day. The hexagon is not a feature that would be predicted by standard fluid dynamics based on simple models. Circular storms are common on planets with rotating atmospheres. Elliptical storms can form under certain conditions with asymmetric heating or Coriolis effects. But hexagons are geometrically unusual and unexpected. How such a precise, regular six-sided shape forms and persists for decades has been the subject of intense scientific investigation by fluid dynamicists, atmospheric scientists, and planetary physicists. Laboratory experiments conducted by multiple research groups have demonstrated that polygonal storm patterns can form when fluid in a rotating container experiences specific conditions involving differential rotation at different depths, where rotation rates vary with depth in the fluid. When fast rotating fluid at the center is surrounded by slower rotating fluid at the edges, waves form at the boundary between these regions. These waves can organize into regular polygonal patterns rather than chaotic turbulence. Saturn's hexagon appears to be a manifestation of atmospheric dynamics occurring deep within Saturn's atmosphere, thousands of kilometers below the visible cloud tops where human observers can see it, suggesting that the visible E-hexagon is the surface expression of deep internal atmospheric structure and dynamics. The sides of the hexagon are approximately 14,500 kilometers long, longer than Earth's diameter, and the entire feature is roughly 20,000 kilometers across. The storm was blue when first observed by Voyager and has changed to a more golden color in recent decades, a color change attributed to seasonal changes in sunlight exposure and atmospheric chemistry as Saturn moves through its orbit around the Sun. This color change indicates that Saturn's seasons, which last more than 7 years, each due to Saturn's slow orbit around the Sun with a period of 29 Earth years, profoundly affect even the most stable and persistent features of the atmosphere. The winds around the hexagon reach speeds of approximately 300 miles per hour, or approximately 480 kilometers per hour, comparable to the fastest hurricane winds on Earth. Saturn's atmosphere is also home to numerous smaller storms and weather systems in addition to the hexagon. Cyclonic systems form in some regions and dissipate over timescales of months to years. Anticyclonic systems persist for years or decades, including storm systems as large as Earth itself. Lightning has been detected in Saturn's atmosphere, evidence of electrical discharge and convective activity in the cloud layers, indicating that the atmosphere is not quiescent, but actively churning with storm systems. The atmosphere is not uniform or unchanging. It is dynamic, complex, and responsive to subtle changes in internal heat transport and solar irradiation. Understanding Saturn's atmosphere requires sophisticated mathematical and computational models that account for atmospheric chemistry involving complex organic compounds, fluid dynamics with multiple interacting wind patterns, thermodynamics with temperature gradients and energy transport, and the interaction between deep atmospheric layers with different compositions and the shallow visible cloud layers. The complexity is substantial, and many questions about Saturn's atmosphere remain unanswered and awaiting investigation by future spacecraft and increasingly sophisticated theoretical models. Saturn's magnetic field represents another frontier of mystery and uncertainty, a realm where observations raise questions faster than theories can answer them. Unlike Earth's magnetic field, which is generated by convection currents in the planet's molten iron core, Saturn's magnetic field must be generated by currents moving through liquid metallic hydrogen existing at extreme pressures deep within the planet's interior. The magnetic field itself is surprisingly weak relative to the planet's size. Jupiter's magnetic field dwarfs Saturn's, despite Saturn being a massive world in its own right. Jupiter's magnetic field is roughly 10 times stronger than Saturn's. Even though both planets are gas giants of comparable size, yet Jupiter receives comparable or perhaps even less solar energy input. The field strength has been measured by multiple spacecraft, including Voyager and Cassini, providing data spanning decades of observation, allowing scientists to determine not just the field strength at particular moments, but how it might vary over time. What has become clear is that Saturn's magnetic field is aligned almost perfectly with the planet's rotation axis. Unlike Earth's field, which is tilted roughly 11 degrees relative to the rotation axis, creating an offset that contributes to the complexity of Earth's magnetosphere. This alignment at Saturn seems almost too perfect to be accidental, suggesting that the mechanism generating the field is deeply connected to Saturn's rotation and interior structure in ways that Earth's more tilted field may not reflect. The dynamo process that generates Saturn's magnetic field involves circulation of conductive fluid in the metallic hydrogen layer, currents flowing in patterns that create the magnetic field through electromagnetic induction, the same principle that powers electromagnetic generators on Earth, where moving conductors through magnetic fields generate electrical currents. These currents must persist over billions of years, sustained by the heat flowing out of Saturn's interior and the mechanical energy of planetary rotation. The precise location of the dynamo within Saturn remains uncertain. Is it in the outer layers where metallic hydrogen first appears? Is it deeper in the interior where pressures and temperatures are extreme? The answer matters because it constrains models of Saturn's internal structure and composition, and because different dynamo locations would imply different circulation patterns and different sources of energy driving the currents. Magnetic reconnection events occur in Saturn's magnetosphere, where magnetic field lines from the planet become tangled and suddenly snap, releasing enormous amounts of energy that accelerates particles to extreme speeds many millions of kilometers per hour, converting magnetic energy into kinetic energy of particles and thermal energy in the process. These events create auroras at Saturn's poles, visible as glowing curtains of light similar to Earth's aurora borealis, or northern lights, but driven by different physics and energized by Saturn's internal magnetic field, rather than by interaction with the solar wind. On Earth, solar wind particles trigger auroras, but at Saturn, the internal magnetosphere provides the energy source. The auroras at Saturn display behavior that sometimes follows a pattern and sometimes behaves chaotically, suggesting complex interactions between the planetary magnetic field, the ionosphere, and the magnetosphere that are far from fully understood. Temperature variations in the auroral region suggest energy deposition that cannot be fully explained by current models of how particles interact with the upper atmosphere, pointing again to missing physics or incomplete understanding of magnetospheric processes. What drives these auroras remains incompletely understood, and why some auroral events are periodic while others are sporadic remains an open question that continues to occupy planetary magnetospheric physicists. The periodicity in some auroral events suggests connections to periodic variations in solar input, or to periodicities in Saturn's own internal energy output. But isolating the actual mechanism has proven elusive, despite decades of observation and theoretical work. Saturn's internal structure presents mysteries as deep and profound as any other aspect of the planet. Unlike Earth, where the interior has been extensively studied through seismology using earthquakes to map density variations and layer boundaries, Saturn's interior remains largely unknown, accessible only through gravity measurements, magnetic field observations, and theoretical models based on our understanding of physics at extreme pressures and temperatures. The core of Saturn is believed to be solid, composed primarily of rocky material and metals, with a mass estimated at somewhere between 10 and 30 times Earth's mass. But this is a wide range reflecting substantial uncertainty among planetary scientists who have spent decades attempting to constrain the core's properties. The exact composition of the core remains unknown. Is it primarily rock, similar to Earth's core? Does it contain significant amounts of iron? How much water ice remains in the core versus being segregated into higher layers? No one knows with certainty. The uncertainties matter because core composition affects how the core formed, where it came from in the protoplanetary disk, and how it has evolved over billions of years. Surrounding the core lies a massive layer of liquid metallic hydrogen, hydrogen compressed to such extreme pressure by the weight of the atmosphere and layers above it that it behaves as a conductor of electricity, allowing currents to flow and generating the magnetic field. The transition from ordinary liquid hydrogen to metallic hydrogen occurs at pressures exceeding 400 gigapascals, which is 4 million times, as Earth's atmospheric pressure. Above this layer lies a region of liquid hydrogen and helium, the source of Saturn's dynamic atmosphere, with these layers merging gradually into the visible cloud layers from which we observe Saturn. The exact depth at which ordinary liquid hydrogen transitions to the metallic phase is uncertain, but it is estimated to occur somewhere between 10,000 and 20,000 kilometers from the planet's center, depending on the actual temperature profile and composition. The pressure and temperature at different depths within Saturn have been estimated through theoretical models and through comparison with Jupiter's structure and properties, but they have never been directly measured by any probe. The highest pressure and temperature conditions have been replicated in laboratories using diamond anvil cells, where incredible pressures, up to millions of atmospheres, are applied to tiny samples. But these experiments can only explore limited ranges of pressure and temperature, and Saturn's interior extends far beyond what laboratory experiments can access. Furthermore, laboratory experiments cannot replicate all the relevant conditions, including the presence of both hydrogen and other elements, in proportions matching Saturn's composition. The temperature at Saturn's core reaches approximately 11,700 Kelvin, roughly twice the temperature of the Sun's visible surface, at about 5,800 Kelvin, yet Saturn has somehow remained stable from early in the solar system's history, without cooling to a frozen, geologically dead state, as simple models might predict would happen to a gas giant over billions of years. This persistent internal heat is one of Saturn's most enigmatic characteristics, distinguishing it from what a simple model of planetary cooling would predict. The planet continues to radiate heat at a rate that suggests ongoing heat generation from somewhere in the interior, not merely the slow dissipation of primordial heat from formation. Gravitational compression provides some heating as Saturn's mass slowly pulls inward, converting potential energy into thermal energy through a mechanism called Kelvin-Helmholtz contraction. But calculations suggest this mechanism alone cannot account for the observed heat output. Helium precipitation offers one explanation for the additional heat. In Saturn's outer layers, where temperatures are cooler than the interior, helium has been slowly condensing from solution in the hydrogen atmosphere, forming liquid droplets that fall downward through the layers below. As these droplets rain down through denser and hotter regions, friction dissipates their kinetic energy, converting the energy of falling material into heat that keeps the interior warm. This process, ongoing for billions of years since Saturn's formation, could potentially account for much of Saturn's observed heat output. The helium rain process also explains why Saturn's atmosphere contains less helium than Jupiter's or than the primordial composition of the solar nebula from which all planets formed. A deficit that puzzled scientists for decades until this mechanism was proposed. Yet significant uncertainty remains about whether helium precipitation alone can fully explain Saturn's heat output, or whether additional processes remain undiscovered. The internal rotation of Saturn has been constrained by recent data from the Cassini spacecraft, providing information about how the planet spins at different depths. The visible cloud layers that we observe in images rotate with a period of approximately 10 hours and 39 minutes at the equator, varying with latitude in patterns similar to Earth's jet streams, but deep inside Saturn, beneath the clouds where human eyes cannot see and where light cannot reach. The rotation appears to be much more uniform with less variation by latitude, suggesting a more stable, less dynamic interior. Gravity measurements from Cassini's grand finale orbits, when the spacecraft flew through the gap between Saturn and its rings in a series of audacious maneuvers, pushing the spacecraft's capabilities to their limits, provided unprecedented precision in mapping Saturn's internal gravity field with accuracy better than ever before achieved. These measurements suggest that the deep interior rotates with a period of 10 hours and 33 minutes, slower than the visible clouds at the equator, meaning the visible clouds are moving ahead of the interior. This differential rotation between atmosphere and interior indicates that the solid or near-solid core may have a different rotation rate than the fluid layers above it, suggesting complex internal dynamics and interactions between different layers that remain incompletely understood. Understanding these differential rotations requires sophisticated models of how Saturn's interior evolved after formation and how tidal interactions with Saturn's moons have affected internal dynamics over billions of years. The discovery of Saturn by ancient astronomers predates recorded history in many cases, but the scientific exploration of Saturn is a much more recent phenomenon spanning only the last few decades of human spaceflight. The earliest telescopic observations came in the 17th century when Christian Huygens first perceived Saturn's rings through his primitive telescope in 1655, though he initially misinterpreted them as a triple planet or as companions orbiting Saturn, rather than recognizing them as a ring system surrounding the planet. The ring's true nature was not confirmed until observations by other astronomers, particularly Giovanni Cassini in the 1700s, suggested the ring structure over subsequent decades of careful telescopic observation. The modern era of Saturn exploration truly began with the Pioneer missions in the 1970s, a series of spacecraft designed to explore the outer solar system when computers were primitive and communication speeds were measured in bits per second rather than the megabits per second of modern spacecraft. Pioneer 10 flew by Jupiter in 1973, demonstrating conclusively that spacecraft could survive the harsh radiation environment of the outer solar system, where charged particles trapped in powerful magnetic fields would bombard any spacecraft with high-energy radiation that could damage instruments and shorten spacecraft lifespans, and could transmit data back across hundreds of millions of kilometers of space with signal strengths measured in watts, tiny fractions of the power of a household light bulb. Pioneer 11 followed, encountering Jupiter in 1974 and then traveling onward to become the first spacecraft to reach Saturn in 1979. A tremendous achievement given that Saturn is much farther from Earth than Jupiter, requiring the spacecraft to travel through empty space for many years, and the spacecraft had to navigate the vast distances of space with primitive navigation systems by modern standards and chemical propulsion systems with finite fuel supplies. The mission provided the first close-up images of Saturn's atmosphere, showing the banded structure and cloud patterns, images of the rings revealing their complex structure, and images of several of Saturn's moons, including Titan and Rhea and others, revealing details invisible from Earth-based telescopes, even with the largest instruments available at the time. Data from Pioneer 11 revealed the complexity of Saturn's ring system in unprecedented detail, showing that what appeared from Earth as smooth, featureless rings were actually composed of thousands of separate ringlets with distinct gaps between them, suggesting that the ring system was far more intricate and structured than anyone had anticipated, requiring new theories to explain how such structure could form and be maintained. The spacecraft measured temperatures, radiation levels, and magnetic field strengths, providing the first detailed scientific measurements of Saturn's environment, rather than relying solely on observations from distant Earth. The Pioneer spacecraft also discovered new moons orbiting Saturn, small bodies previously invisible from Earth that required close-up imagery and sensitive detection instruments to identify. The discoveries demonstrated that Saturn's moon system was far more complex than previously understood, with numerous small bodies orbiting in addition to the larger moons known from Earth-based observations. Pioneer data suggested that the rings themselves were dynamic, not static structures that had remained unchanged for billions of years as previously thought, with particles constantly colliding and exchanging momentum, indicating that the ring system was an active, evolving environment rather than a static relic of planetary formation. The Voyager spacecraft missions brought an unprecedented leap in understanding in the early 1980s. Voyager 1 encountered Saturn in 1980, approaching to within approximately 77,400 kilometers of the PE, Planet's center, an incredibly close pass that provided the most detailed images and measurements yet taken. Voyager 2 followed in 1981, taking a slightly different trajectory that allowed it to continue onward to Uranus and Neptune, exploring the outer solar system beyond Saturn in a grand tour of the gas giants. The Voyager missions revealed the fine structure of Saturn's rings with astonishing clarity, showing subtle details that had remained completely invisible to all previous observations made from Earth or by earlier spacecraft. Images showed spokes extending radially outward from the planet's equator, ghostly structures visible against the rings that appeared and disappeared on timescales of just hours, completely unexpected by scientists preparing for the Voyager encounters and representing one of the most surprising discoveries made during the Voyager mission to Saturn. Thousands of individual ringlets became visible in Voyager images, showing that Saturn's rings possessed far more complex and intricate structure than anyone had anticipated, with patterns suggesting dynamic processes operating within the rings continuously. The discovery of new moons continued with both Voyager spacecraft, revealing a system of small satellites orbiting Saturn in the region of the rings, including shepherd moons whose gravitational effects shaped the ring structure and kept particles confined within specific regions of space. The Voyager missions also provided detailed studies of Titan, revealing a moon so different from any previously studied that it captured scientific imagination immediately upon release of the data. The cloud-shrouded surface visible to Voyager suggests a world fundamentally different from other moons, a place where exotic chemistry might operate under conditions never before directly observed by human spacecraft or instruments. The atmospheric measurements from Voyager showed nitrogen as a dominant atmospheric component with smaller amounts of methane and other organic compounds, revealing an atmosphere far more substantial and complex than initial estimates had previously suggested. The gravity measurements provided the first good estimates of Titan's mass, showing it to be enormous, larger than Mercury, far larger than Earth's moon, confirming that Titan was truly a world unto itself, rather than merely a large asteroid or captured comet. The Cassini spacecraft mission represented the culmination of decades of planning and represented a technological achievement of extraordinary sophistication, spanning multiple countries and numerous institutions. Launched in 1997 aboard a Titan IV rocket from Cape Canaveral, Cassini underwent a complex trajectory through the inner solar system, using gravity assists from Venus twice and Earth once to gain the momentum necessary to reach Saturn's orbit with sufficient fuel reserves to execute the complex orbital maneuvers necessary once arriving at Saturn after a journey spanning years through the solar system. The spacecraft finally entered Saturn orbit on July 1, 2004, beginning a mission that would fundamentally transform our understanding of Saturn, its rings and its moons, providing data that scientists continue analyzing decades later. The mission lasted 13 years, far longer than the original planned mission duration of approximately 5 years, with the spacecraft gradually spiraling inward towards Saturn as fuel was consumed in orbital maneuvers that brought the spacecraft closer and closer to the planet. The extended mission allowed Cassini to observe Saturn through multiple seasons and to track changes in the system over extended timescales impossible for brief flybys. The Cassini mission provided an unprecedented level of detail about Saturn and its system, revolutionizing our understanding of the planet and its environment. High-resolution imaging revealed the rings in extraordinary detail, showing subtle structures invisible from space probes visiting briefly, revealing spiral waves in the rings caused by nearby moons, revealing subtle color variations indicating different compositions, revealing the dynamic nature of the ring system. Time-lapse imaging over weeks and months captured the motion of ring particles, demonstrating that the rings are not uniform or static, but display waves and gaps and asymmetries indicating dynamic processes occurring constantly. Hundreds of individual moons were identified and tracked by Cassini's cameras, allowing determination of their masses and orbital parameters with precision far exceeding previous measurements, revealing orbital characteristics that provided clues to the moon's origins and evolution. The rings were observed to interact with moonlets, with gravity from small moons creating waves and gaps in the ring particles, visible as patterns in the ring structure that allowed scientists to infer properties of unseen small moons through their gravitational effects. The Cassini spacecraft carried a suite of sophisticated instruments, including imaging cameras with extreme resolution, spectrometers analyzing light at different wavelengths to determine composition, magnetometers measuring the magnetic field in 3 dimensions, plasma sensors detecting charged particles, and a variety of other sensors designed to measure properties of Saturn's environment. The data returned filled multiple terabytes of information, yields of data far exceeding anything previous spacecraft missions had delivered. Data that planetary scientists continue analyzing years after the mission ended, discovering new insights from reanalysis of the existing data. The Huygens probe, a separate spacecraft carried aboard Cassini as a piggyback payload, descended through Titan's atmosphere and landed on the surface in January of 2005, the first soft landing in the outer solar system and one of the most ambitious exploration efforts ever undertaken by humanity, requiring unprecedented precision in aiming and execution to land in the correct location after years of coasting through space. Huygens revealed Titan's surface composition through direct sampling and analysis of surface materials, measured atmospheric properties at different altitudes as it descended through hundreds of kilometers of atmosphere, detected organic compounds in the atmosphere including hydrogen cyanide and propylene, indicating complex chemistry, and returned images of a landscape featuring channels suggesting liquid flow at some time in the past, fields of organic dunes organized by wind patterns, and a surface of remarkable complexity suggesting active geological processes, or at least ongoing erosional and depositional processes. The data from Huygens transformed Titan from a fascinating mystery, visible only through Cassini's imaging systems, and completely obscured by atmospheric haze, to an accessible world with detailed maps and measurements of the surface, allowing scientists to plan future exploration missions and to develop more detailed theoretical models of Titan's evolution and current state. The Cassini orbiter continued observing Titan for years after Huygens landed, revealing lakes and seas of liquid hydrocarbons at the polar regions, confirming the existence of surface liquids and demonstrating that Titan possessed the most Earth-like hydrological cycle in the solar system beyond Earth itself. Cassini also explored Enceladus extensively with dozens of close flybys during the mission, revealing the geysers of water ejecting from the South Polar region, discovering the subsurface ocean through gravity measurements, and detecting organic compounds in the geyser material, opening the possibility that Enceladus might harbor life and establishing Enceladus as a priority for future exploration. The Cassini mission provided data about Saturn's magnetic field and magnetosphere that exceeded anything that earlier spacecraft had measured, revealing the field's structure and variations over the mission. Multiple close approaches to Saturn and detailed mapping of the magnetic field structure revealed complexity in how the field interacted with the solar wind and Saturn's moons. The gravitational field of Saturn was mapped with unprecedented precision during the grand finale phase, when Cassini flew repeatedly through the gap between the planet and its rings in a series of 22 orbital passes, each bringing the spacecraft closer to Saturn's atmosphere, allowing constraints on internal structure that would have been impossible without the careful orbital tracking of Cassini's position through the gravity field as the spacecraft orbited Saturn hundreds of times over the 13-year mission. Each pass through the ring gap allowed new measurements of the gravitational field at different locations, building up a 3-dimensional map of how gravity varied throughout Saturn's environment. The data from these measurements continues to be analyzed by scientists seeking to understand Saturn's internal composition and structure. Yet despite all that Cassini revealed and all the data scientists have collected over decades, fundamental questions about Saturn remain unanswered and continue to occupy the attention of planetary scientists worldwide. The precise mechanism that generates Saturn's magnetic field is still not fully understood despite the theoretical frameworks and models available. Why does it persist so strongly? Where exactly is the dynamo region where currents flow and generate the field? How deep into Saturn's interior do currents flow to generate magnetic effects? How does the rotation of the core relate to the generation of the field? No one can say with certainty, and different models propose different answers. The composition of Saturn's interior beyond the outermost layers remains uncertain in crucial details. What is the core made of? How large is it? Is it primarily rocky material? Does it contain significant amounts of iron? Are there water ice layers? These basic questions lack definitive answers, despite the constraints provided by gravity measurements. The mechanism that generates Saturn's enormous internal heat remains incompletely explained, despite decades of theoretical work. Helium rain explains part of it, but does it explain all of it? Possibly not, and the excess heat over predictions continues to puzzle scientists. Saturn's atmosphere continues to puzzle scientists, even after extensive observation. Why does wind speed vary so dramatically with latitude, creating the banded structure we observe? Why do some storms persist for decades, while others vanish in weeks? How exactly do the jet streams at the surface interact with deeper layers, where the composition changes and where densities vary? The hexagon remains perhaps the most visually striking unsolved mystery of all Saturn's features. No other planet displays such a geometric phenomenon, making Saturn truly unique in this regard. The mechanism that generates and maintains the hexagon involves physics we understand partially but not completely, with laboratory experiments providing hints but not complete understanding. The precise origins of Saturn's rings remain debated among planetary scientists. Are they truly only 100 million years old, as Cassini data suggests? The evidence seems to support it, but alternative theories propose older ages, and the debate continues. The dynamics of ring particles continue to surprise observers with unexpected phenomena. Spokes appear and vanish on hourly timescales. Gaps form and persist or change. Wave patterns propagate around the rings at different speeds depending on their origin. The mechanisms driving these phenomena are understood partially, but surprises continue to emerge from detailed observations and continue to challenge our understanding. The nature of Titan's methane cycle remains one of the most fundamental unresolved questions about the Moon. Where does the replenishing methane come from when it is continuously destroyed by sunlight? Cryovolcanism? Outgassing from frozen methane clathrates? Biological processes producing methane from microbial metabolism? The answer eludes scientists, despite many decades of speculation and investigation. Titan's subsurface ocean remains unobserved directly, unknown in its fundamental properties. How deep is it? How warm? Does it contain hydrothermal vents that could provide energy for life? How might exotic life adapt to such an environment based on water and ammonia, rather than the water and salts of Earth's oceans? We can only speculate based on indirect measurements and theoretical models. Enceladus's ocean raises similar questions about subsurface environments. The geysers prove liquid water exists beneath the icy surface, but the exact composition, temperature, and circulation patterns of the ocean remain incompletely understood. The source of energy maintaining the ocean against gradual cooling is tidal friction from Saturn's gravity. But the precise balance between heat generation and heat dissipation remains uncertain. Saturn's moon system continues to reveal surprises as survey techniques improve. The recent discovery of over 100 new small moons in 2025 suggests that Saturn's system is far more complex than previously realized. How did so many small bodies come to orbit Saturn? Were they captured from elsewhere in the solar system? Did they form in situ from material in Saturn's original disk? The orbital characteristics of the newly discovered moons provide clues about their origins, but the full story of how Saturn acquired such a large and diverse moon system remains incomplete and awaits future investigation. Saturn, in many ways, represents the frontier of solar system exploration, a world that has yielded remarkable discoveries while simultaneously revealing how much remains unknown. Despite decades of study by multiple spacecraft, including Pioneer, Voyager, and Cassini, fundamental questions about Saturn persist and continue to occupy scientists. The planet's mysteries remind us that understanding planetary systems requires sustained effort, sophisticated technology, and persistent curiosity maintained across generations of researchers. Saturn continues to fascinate astronomers, planetary scientists, and the general public alike, capturing imaginations through its beauty and through the profound questions it raises. The rings capture imaginations with their delicate structure and breathtaking appearance. Titan beckons with its exotic chemistry and potential habitability, a world more Earth-like than anywhere else we have found beyond our home planet. Enceladus suggests that life might exist in worlds beneath frozen surfaces in oceans we cannot directly observe. That habitability may be far more widespread than earlier scientists expected. Saturn's internal heat generation raises fundamental questions about planetary formation and evolution, about how planets acquire energy and maintain it for billions of years. The hexagon remains an icon of the unexpected wonders that await discovery in the cosmos, a reminder that nature produces phenomena we could not predict or fully explain, despite our sophisticated understanding of physics. Future missions will continue the investigation of Saturn's mysteries through sustained exploration. Planned orbiter missions to Titan will arrive in coming decades, including NASA's Dragonfly mission that will deploy rotorcraft to explore multiple sites across Titan's surface, collecting samples and searching for evidence of life or prebiotic chemistry. Probes will descend through Enceladus's geysers, sampling the water and organic compounds directly, potentially detecting life if it exists or biosignatures if life once existed. Sophisticated instruments on future spacecraft will measure gravitational fields and magnetic properties with even greater precision than Cassini achieved, constraining internal structure models and allowing better estimates of core properties. Advanced spectrometers will analyze compositions of atmospheres and surface materials with finer detail. Yet even as we plan these future missions, we must acknowledge that Saturn may continue to surprise us, that nature may continue to confound our expectations and force us to revise our understanding. Science progresses not through the accumulation of absolute certainty (BGE), but through the systematic reduction of ignorance, answering old questions only to reveal new ones waiting beneath the surface like geological strata beneath the soil. Saturn, with its rings and storms and mysterious interior and moon system of astonishing complexity, stands as a monument to the vast domains of knowledge still waiting to be explored, still waiting to be understood, still harboring secrets that future generations will discover as they continue humanity's endless journey to comprehend the cosmos. The planet will continue rotating steadily on its axis, radiating heat into the vacuum of space, its hexagon spinning at the North Pole, its rings raining particles downward in a slow descent, its moons orbiting in their prescribed paths determined by gravity, all of it governed by physics we understand partially, and by mysteries we have yet to penetrate or even properly formulate. Saturn is not finished revealing its secrets. The investigation continues, will continue for decades and centuries to come, as humanity extends its reach into the outer solar system, and as our instruments become ever more sensitive and sophisticated. The mysteries of Saturn call to us across the vast distances of space, reminding us that the universe contains wonders beyond imagination and knowledge beyond our current grasp.